So let's begin with the lecture first. So chapter 4 is all about thermodynamic equilibrium. Right now in front of you I have a figure of two guys on a seesaw and this is an unbalanced situation right now. So one guy is high on elevation, the other guy is low on elevation. Is this on an equilibrium position or is it in a non-equilibrium position? So seeing this visually, we can clearly say it is an equilibrium position. It's in a non-equilibrium position, at least on Earth. And why is that? Because one guy has a much higher potential energy, the other guy is on the other side, and let's say they both weigh same, but he's has lower potential energy until or unless they both come at the same height, have the same potential energy, this won't come in a equilibrium states. So this is what a equilibrium is. Similarly, thermodynamic equilibrium. What thermodynamic equilibrium means is if we remember in the last lecture, we studied thermodynamic properties. So properties are the characteristics of a thermodynamic system. So if I want to define the characteristic or the state of a system, I will use thermodynamic properties as my tool. I will say this is the temperature, I will say this is the pressure, all that. So similarly, the thermodynamic equilibrium, we can define thermodynamic equilibrium is achieved or it's a state when there is no change in the macroscopic properties is observed. So if I'm seeing something and I see there is no change in the system, and if it is isolated from the surrounding or it is not isolated from the surrounding, both the cases, even if it is isolated, if it is not isolated, I see there is no change in the state of the system, I can say that it's in a thermodynamic equilibrium. Now, the question arises, when does a system reach or thermodynamic equilibrium, or when do we reach thermodynamic equilibrium? So we reach thermodynamic equilibrium when we achieve mechanical, chemical, and thermal equilibrium. So when we achieve mechanical equilibrium, what does that mean? So mechanical equilibrium means if I have a system, let's say this is a system here, and this is the surrounding, this is the system boundary. So I can say the mechanical equilibrium is achieved when I clearly see there is no mechanical transfer or there is no force transfer, there is no pressure transfer, any change in mechanical properties. So we are seeing no changes in the mechanical properties. I can say this is in a mechanical equilibrium. When does we see a chemical equilibrium? If I see any change in the chemical composition. So what does a chemical composition means? Let's say I have this system is comprises of 70% oxygen and let's say 30% carbon dioxide, whatever, just for as an example right now. So if I see there is some change in the chemical composition, at some point it reaches 80% oxygen and 20% CO2 when I expose this to surrounding. So this is a change in chemical composition. So I cannot say this has achieved equilibrium state, a chemical equilibrium state as of yet. So until or unless when I expose this system to surrounding and I see there is no change in the chemical composition of the system, I can say this is in chemical equilibrium. Now, what does a thermal equilibrium means? I can say the system is in thermal equilibrium when I see, let's just rub this thing, and I bring here different color. So when I see this system has a temperature T, or let's say T1, and the surrounding has a temperature T2, and I expose this system to the surrounding. Earlier it was, let's say, isolated, but then I removed the isolation wall and I say this system is now exposed to the surrounding. Is there a transfer of heat taking place between the two systems? Because T1 and T2 could be different, could be same. If they are same, there will be no heat transfer occurring, and we can say this state or this system has reached a thermodynamic or a thermal equilibrium. But if there is a heat transfer taking place, so until the T1 becomes T2, or the system and the surrounding together comes in a equilibrium position, I cannot say this is thermal equilibrium. So until that happens, this will remain in a non-equilibrium position. So a thermal equilibrium is achieved when we have no change in temperature and no heat transfer taking place along the walls of the system. That's a thermal equilibrium. Now, since we read this, how do I know what is a non-equilibrium state? So I was talking about, okay, thermodynamic equilibrium. We know what is a thermodynamic equilibrium. Thermodynamic equilibrium is achieved when a mechanical, chemical, and thermal equilibrium is achieved. Only then a thermodynamic equilibrium is achieved. This is very important, guys. For a thermodynamic equilibrium to take place, all the three equilibrium should be there: mechanical, chemical, thermal. If one of them is not there, we cannot say a system is in thermodynamic equilibrium. So clearly now it's an easy definition for non-equilibrium state. If there is any unbalance in interior force, or let me say, if there is any mechanical non-equilibrium, if there is any chemical non-equilibrium, if there is any thermal non-equilibrium, we say this is a non-equilibrium state of a system. So for a mechanical, if there is any unbalance in the interior force or in between the system and the surrounding, this will be a mechanical imbalance. If there is an unbalance in temperature or there is unbalance in the temperature of a system and the surrounding combined, we say this is a thermal non-equilibrium. And then comes chemical non-equilibrium. Similarly, if there is a disbalance in the chemical composition of the system and the system and surrounding combined, we say that's a non-equilibrium state. One important thing to note, if there is a unbalance, if there is a thermal unbalance, you cannot define the state of a system by a single temperature. What does that mean? Let's say this metal is there. This is a metal surface and I'm heating it right now. Okay, I'm heating it right now. But this metal surface has some deformities inside, or I don't know, some aliens dropped it here. And now we are seeing that this metal surface, when I calculate temperature at this point, I'm getting T1. When I'm getting at this point, I'm getting T2. When I'm calculating this point, I'm getting T3. It could be different. So until or unless, if I'm taking this whole as a system, I cannot say the temperature is T1 plus T2 plus T3 and then average it. That's not possible because it is undergoing a change of temperature. So until or unless all these points just became one and I reach a single temperature state, capital T or whatever, the thermal equilibrium is not achieved. So this is going through a distribution of temperature, and we will see a temperature profile. So if I plot temperature here and try to see how this is varying with time, so this is time and temperature, I might see at 1 minute, 2 minute, 3 minute, 4 minute, I see the temperature of this system is decreasing or it might be increasing, whatever. Until it reaches equilibrium state, I cannot say this is in thermal equilibrium. And I cannot say the system temperature is equal to a particular specific value. So it is very important, guys. It is very important. We approach our next question and why we are reading this thermodynamic equilibrium. When does thermodynamic properties cannot be used to define a system? This is why we are reading thermodynamic equilibrium, why we are trying to understand this, because your classical and statistical thermodynamics, they make use and they assume that the system is in a thermodynamic equilibrium. So for using equations in classical or statistical thermodynamics, you need to have a thermodynamic equilibrium. That's why any system which has a non-equilibrium state, we don't have equations for that in statistical or classical thermodynamics. This is what we are reading. We are reading classical thermodynamics. So we don't have equations for any non-equilibrium state right now in this subject, in the subject which we are reading. We don't have any equations for that. So for defining any equation or using any equation or any theorem, any formula, you need to have a thermodynamic state or a thermodynamic equilibrium. That's why this becomes important. So this is the reason why a thermodynamic equilibrium is studied and why the mechanical, chemical, thermal equilibrium has to be achieved in a system before we move forward. So I hope you like this video, and if you feel like this was something useful, please hit like and subscribe to the channel. This encourages me to put on more videos like this. Also share it among your friends, colleagues who can benefit from this lecture series. And we will see you on the next lecture, which is chapter 5, which is going to be on quasi-static process, a very important process in thermodynamics, and why it is important to understand that, how thermodynamic equilibrium plays a role in quasi-static process. This all we will see in the next lecture in chapter 5. Till then, have a good day, guys.